Hello and welcome to this Nordic Tech webinars. Today's topic is adding battery charging and fuel gauging to your nRF52 series project. My name is Robin M. Saltness. I am a senior product marketing engineer here at Nordic Semiconductor, and I will be the host and presenter of today's webinar. So here's the agenda for today's practical demonstration. First, we will look at the NPM 1300 EK and the NPM PowerUP desktop software. So we'll show you how to set up and connect your NPM 1300 EK to a PC, and we will go through all the features of NPM PowerUP. Then we will show how you can use the NPM 1300 evaluation kit with an nRF52 development kit by adding basic PMIC functionality via exporting from NPM PowerUP into VS Code, and this way implementing the PMIC settings into a sample that doesn't have PMIC functionality in it from before. We will also look at fuel gauging, namely we will show how you can characterize a battery in NPM PowerUP and how you can add fuel gauging to any nRF Connect application. But first, how do you charge a battery and estimate its state of charge? Well, you add a PMIC. And the NPM 1300 PMIC is the perfect PMIC to do just this. It has two ultra-high efficiency buck regulators that could power your SoC and other components in your system. It has obviously a battery charger. It has some other unique system management features not found in other PMICs as well. One of these being the accurate ultra-low power fuel gauge that we will show you how to use in this webinar. For the hardware side, you need to make some connection between your NPM 1300 and your nRF52 series SoC to get this to work. For once, you need to make a TWI, so I2C connection between the PMIC and the SoC. So here we have used the port 026 and 27 on the nRF52 832 and connected them to the SDA and SCL pins on the PMIC. Then we are powering the nRF52 series VDD input via buck 2, so Vout2 on the PMIC. This is also powering the I/O of the PMIC, so these are connected together. Then we have a port 022 on the nRF52 SoC that is connected to GPIO3, which is sending interrupts for the first sample we will look at. Okay, since this is a practical webinar, we will go straight into the practical demonstration. So when evaluating the NPM 1300 to see if it's the right product for your application, you would probably use the NPM 1300 evaluation kit. It has the NPM 1300 PMIC right here, and inside the white square is all the component needed to make the PMIC fully operational. It also has a nRF5340 SoC that acts as an interface between your PC's USB and the TWI interface of the PMIC. All the components associated with this interface is inside this white line here. And to connect to NPM PowerUP PC application, we connect the NPM controller SoC to the PC with a USB-C cable. The kit also features buttons that are connected to all the GPIOs of the PMIC. You also have access to all the pins on the PMIC itself on the side here and here. The outputs of the bucks, the bus, V-bus voltage, system voltage. You have battery connectors for different types of batteries. You have a charge power, so a USB connection to the PMIC itself, which is needed for charging batteries because you do not take power from anything else than the interface SoC from the PC that you're connected to. And you also have 3 LEDs for error charging and host control. They can be disconnected with these jumpers to eliminate current draw from them. And we also have these jumpers that puts the load switches in series with a small and big resistors that can act as current sinks when evaluating the PMIC under different loads. So once we have connected the kit to a PC, we will open the NPM PowerUP application that is found inside nRF Connect for desktop. And we can see that our device shows up here under select device. We selected, and we see it says PMIC not powered, which means that we need to actually power the PMIC separately from the USB connection. So for this, I will use a battery. I will connect the battery here through the battery connector. Keep in mind that this connector is positive bottom polarity. So there are incompatible batteries out there, so be aware. You can see PMIC is not powered by USB, which means that we cannot enable charging. To enable charging, we will have to connect to a high quality USB power source. This can just be a power brick because it's no data needed to charge devices. So here I have a USB-C that is connected to a high quality USB-C power source. And you can see that the current consumption of the PMIC goes down from 1 milliamp-ish, which is not really accurate, down to 0 when you connect this power supply. And that is because this current consumption is only showing what is going out of the battery or into the battery when you're charging. If you want to use the charger, you set the correct termination voltage. So this is a 3.7 volt nominal battery, which means it has a termination voltage of 4.2. And because it's a 1350 milliamp battery, I can set it all the way up to 800 milliamps of charging current. Then I enable the charger, and you can see that the time to empty changes from time to empty to time to full, and you will see that the state of charge will start rising. From this main dashboard, we can also adjust the voltage of the bucks, buck 1 and buck 2, and the voltage of LDOs when they are driven, or load switch on off when they're not driven. The fuel gauge relies on this battery model. So for this kit, we have already injected the LP803448 LiPo battery, which is the one that most closely resembles the battery that I'm using for this demo. We also have some other brands and models bundled with the app, namely some from LiPo and some from Renata. And to change out the battery model, you simply select the model and manufacturer from the list, and you select write battery model, and you write it to an empty slot in your kit. And this will change how the fuel gauge and time to empty responds. So you see it dropped now because we're using the wrong model for this battery. In the other tabs of this application, you find more advanced features of every aspect of the PMIC. So we have more advanced charging features. Let me just remove the camera. More advanced features of the charger. For example, you have the termination current 10 or 20%. This is the current you charge at when you're reaching full. Same with the trickle fast. It's the voltage you're charging at when you are trickle charging at low voltages, so when the battery is close to empty. The charger thermal regulation is the junction temperature of the PMIC, so here it will stop charging at 109 degrees and not resume again until you drop below 100. This is adjustable. And you also have the JETA compliant monitoring for the battery thermistor, which has 4 different levels. That's also possible to set. And we also can change the NTC thermistor parameters. So this battery has a 10 kilo ohm resistor, so this is correct. But there are also batteries out there with 47 kilo ohms and 100 kilo ohms. And if you're using a battery without a thermistor, you can use ignore NTC. For the regulators, we have more advanced settings for the buck 1, buck 2, and the load switches. For example, you have a retention voltage, which is a voltage that you can set your PMIC to go into when the rest of the system is sleeping. We have mode control, so you can force PFM or PWM modes, or you can make the mode be controlled by GPIO input. Same with on-off control and with retention control, which is when you go into this retention mode. Load switches have soft start current settings up to 50 milliamps, and it also has active discharge and on-off control like the bucks. GPIOs, the system has 5 GPIOs that can be used for different things, like output interrupts or inputs, and output the power loss warning that I'll talk about a little bit later. And it also has the 3 LEDs on the kit, which can be configured. So the LED 0 is red and it's currently charger error. LED 1 is green and is charging, and LED 2 is yellow and it is host controllable. If I change up charger error and charging, you will see that going back to the camera and enabling the charger makes the red LED on the kit light up. As before, it was the green one. Put it back. We can see that now it is the green one that lights up. Other system features that are interesting in the NPM 1300 PMIC is the long press reset, which is a 10-second reset that makes the PMIC power cycle. This can be configured to work on only one button, one GPIO on the PMIC, or you can actually require 2 GPIOs to be pulled load for this to take effect. Then you have ship and hibernate mode, which are ultra low power sleep modes that makes the whole system power off and allows you to power back on again with just a button press. The same button that is used for long press resets, by the way. So the time this button needs to be pressed for you to enter active mode from ship is also fully configurable from 16 milliseconds to 3 seconds or so. And you can also enter these modes in this app. Just remember that you will lose connection to the PMIC when doing so, because it's in sleep. Hibernate mode is a 500 nanoamps sleep mode, while the ship mode is 370 nanoamps. When in hibernate mode, you can use this timer to wake up after a certain amount of time. Like, for example, 1 second. And this timer can also be used for other things like boot monitoring, so waiting for an act from your SoC, for example, to see that it has booted correctly, and if not, it will try to boot again. Then you have the watchdogs and GPIO, general purpose timers that can be used in your system as well. Power off failure is a very interesting feature which allows you to recognize if a battery has been disconnected before actually the system runs out of energy in its capacitors. This means that you, for example, could save settings of your system after it has been completely unplugged from any power source. And this uses a GPIO because any sort of I2C communication would be way too slow. You can also set the polarity of this signal. Here we see the USB detect status, which I will demonstrate a little bit more. So it is currently set to 3 amps high power, which means it has a good USB-C power source. It makes the system able to go up to 1.5 amps of current draw into the PMIC, which means you have 800 milliamps for charging battery, and then the rest is for powering any bucks and LDOs. If I, for example, unplug this high quality power source and plug it straight into my PC using a USB-C to USB-C cable from my USB-C port on my PC, you can see that I get 1.5 amp high power because this is the maximum my PC can deliver. And if I am a pleb and I want to power it from a USB-A power supply, most of you know already probably that these are limited to 100 or 500 milliamps on the USB-A spec. You can see that the PMIC will also discover that. But I like having all the power available, so I will use the high quality power supply for this demo. Then you have a tab called Profiles, which shows you the battery profiles that you have created using the fuel gauge here. We will come back to this later in this webinar, but you can also see that even if we have no custom profiles that we have created ourselves here, we can look into the bundled LiPo and Renata battery models and actually save these to the PC to use these in a VS Code application. In the graph view, we see the output of the ADC in the PMIC, so the voltage of the battery, the current going out from or into the battery, the temperature of the NTC and the state of charge. And in the feedback tab, we can give feedback on our experience with the app. So when you're happy with all the settings you have made in NPM PowerUp and want to use them in a VS Code application, you can click on Export Configuration here in the sidebar. It will give you the option of saving either as a overlay file, which is what you would use in your VS Code application, or you can save as a JSON, which is what you would use if you want to export and use these settings or edit these settings further in NPM PowerUp. In the sidebar, we also find the button for loading these configurations from the JSON file. You can open a serial terminal to look at the same info as in the graph view, but in a serial terminal format. You can reset the PMIC and the controller, and you can also click on record events, which is useful if you want to contact tech support for any reason about this product. And the next thing we'll do is we'll look at the nRF Connect SDK application that is actually using the PMIC in a more realistic way. So to demo how you would prototype an application like this, I have the nRF52 DK that's pre-flashed with a one-button sample for the NPM 1300, which is available from nRF Connect SDK version 2.6.0 and onwards. And to use it, you have to do 5 connections from the EK to the DK. So first of all, you have to do the I2C pins, connecting to the SDA and SCL on the EK, and to pin for this DK, it's 26 and 27 up here. Then these, of course, need a common ground with the DK. I will use this yellow wire here. And then we also need an interrupt pin from GPIO3 to pin 22 on the DK. And that's all the data connections. And then we also need to power the SoC on this DK, and we will power it from buck 2 on the EK. So V out and ground to VDD and ground on the SoC. And we can see here that once powered, this LED starts blinking, flashing. And what's happening is that the PMIC is supplying the SoC with power, and SoC is sending I2C messages to the PMIC to turn on and off the LED driver inside the PMIC. There's also more functionality implemented in this sample. So, for example, if you do a short press on the ship hold button of the PMIC of the EK, you can see that the LED starts flashing faster. And if you do a longer press, it goes back to the slow flashing. And if you do an even longer press, you put the PMIC in ship mode, which is an ultra low power state that powers down the whole system. And in this state, the whole system is just using 370 nanoamps of power. But it's still able to be woken up by a press on the ship hold button. And this is a good example of how many modern applications work. They might just have one button for input, which functions as both input for different features when the power device is on, and also acts as the power switch for the whole system by doing longer presses. But this is, of course, when using a pre-made sample just for the NPM 1300 PMIC. How would you actually implement the functionality of the PMIC in a bespoke application that you maybe made just for the nRF52 SoC? Well, to show you that, we will disconnect from the EK for a while, and then I will connect the DK to my PC. And what we will be doing is that we will open VS Code and we will create a new application. I will copy a sample. I will copy the LED button service sample. And this is a very nice sample that you are showing off. It's a Blinky for Bluetooth, so it comes with its own app that you can use to control the LED on and off on the DK. Add it to workspace. And then we will create a new build configuration for this. nRF52 DK. Then we will build it. Notice that I did not modify this sample at all. Okay, when the sample is built, we're just going to directly flash it to the dev kit. And we can see now that the kit is flashed, this LED starts blinking. And we can also connect to this kit via Bluetooth. I'm not going to do that right now because it's not relevant for this. So let's see how it works if we try to power this with the NPM 1300 EK. So let's get the EK back in here and do all the same connections as we did with the one button sample. So we're connecting I2C pins. We're connecting the common ground. We're connecting pin 22 to the interrupt pin. And we're powering the kit. And we can clearly see here that the DK lights up and the sample is working. So it's all well and good. You don't need to configure the PMIC at all. Well, turns out if we want to, for example, charge the battery here by connecting a power source, nothing happens because the charger is one of the things that actually need to be enabled via the I2C before it takes effect. Which means that there needs to be some sort of communication on these lines, and that isn't set up on this sample by default, and it won't be set up on your application by default. So how do you add the NPM 1300 communication to your sample without breaking whatever else your sample is doing? Well, it turns out it's pretty easy. So what we will do is we will go back into npm PowerUp and we will set all the settings. We don't even need to connect to the kit. We will set all the settings that we want to be used in our application. So we want to charge the battery back up to 4.2 volts at 800 milliamp hours because we have a quite large battery. We want buck 1 to be initialized at 2.5 volts after startup. We want the buck 2 to be initialized to 3.3 volts after startup. And this is the voltage that it will be set to after being set to the voltage determined by the R set resistors on the kit, which you also need to put into your hardware design. Other features you might want to take advantage of is, for example, let's just for the sake of it, change LED 0 to charging and LED 1 to charging error. So they have different colors, so we will be able to see that actually our changes took effect. And when we're happy with the settings, we just export this configuration. And we select the overlay file type, and we put it into the directory of our application, like this. Then we go back into VS Code. We edit our build configuration so that this overlay is a device tree overlay in our build configuration. Then it will do a pristine build again. There are some more configurations we need to make. One of them is that we need to enable the PMIC features in the kconfig. So I have a little cheat sheet here with the kconfigs that I need to put in to make this sample work. So you need to enable GPIOs, enable the shell, configure logging, configuring the regulators and the sensor and the LEDs. And this pulls in all the relevant functionality from the Zephyr project that you need for the PMIC to work. And then there's one more thing we need to do, and that's that we need to configure the I2C port on our DK to have pull-up because the EK or the DK don't feature pull-up resistors. This will suck power, so it's better to have internal pull-up on the kit. And you can do that by going into the overlay and adding these lines at the end. And then we will do a pristine build. Then we can flash this latest build to the 52DK. Let's unpower the PMIC while it's flashing. Okay, the kit has finished flashing. You can see that the light has started blinking again. So let's see if we have succeeded. So let's just power back on the PMIC. We can see the sample is running, and let's now see if the battery will start charging once we connect it to power. And it does, and you can see that it's the red LED that we configured in PowerUp that lights up instead of the green LED that's normally indicates charging. So that's a success, and that's how easy it is to implement NPM 1300 functionality in any previous existing nRF52 or nRF53 series firmware that you have. We did not need to touch our main C files at all. However, if we want to implement more of the dynamic features of the PMIC like we saw in the one-button sample where you use the GPIO for inputs and entering chip mode, then you would have to do some in your C files as well. But for the base configurations, enabling charging and so on, the static functions can be enabled just by the overlays from NPM PowerUp. One of these features is the fuel gauging functionality of the NPM 1300. It works algorithm based, so it uses the ADC that's built into the PMIC, and it runs a fuel gauging algorithm on your connected SoC. If you want to just test it out, you can use one of the default battery models that are found inside the NPM PowerUp application. What you do is you go here and you select your battery manufacturer and the model that most closely resemble the capacity of your battery. Then you select a slot on your kit and write the battery model to this. And you see that the estimation of battery state of charge and time to empty changes based on which model is selected. If you don't find a model that closely resembles your battery, you have to generate your own battery model. And to do that, you need the NPM 1300 fuel gauge board in addition. So here I have prepared my kit with the NPM fuel gauge board and connected it to the NPM 1300 evaluation kit. The way to profile a battery is to go into NPM PowerUp with this connected, select Profile Battery, and you name your battery. I'm naming my Leopold 1350, which is the battery I have. This is a 3.7 volt nominal battery, which means it terminates normally at 4.2 volts. I want it to stop discharging at 3 volts. This battery is 1350 milliamp hours, and because this battery is so big, I can charge it at the full rate. The built-in thermistor of this battery is 10 kilo ohm. You can also select others, and you can ignore NTC if you're using a 2-wire battery. Then you profile this battery at room temperature. You also want to profile it at a low temperature. I'm selecting 5. And then you also want to profile at a high temperature. I will select 45. So you have 20 C increments. Then you select the folder where you want your battery model to be stored. I'm storing mine in a folder I've named My Models. And then you have to connect power to the PMIC so you can fully charge the battery. You want to do this in a temperature chamber, not on your desk like I'm doing now, but this is just for demonstration purposes. Then we click continue, and what happens here is that the battery will start charging your, the PMIC will start charging your battery full. Once it's fully charged, it will start discharging. And when it's at 3 volts, it will start recharging again, but in between you will get a message to change the temperature of your temperature chamber. So this process, discharging and recharging your battery again 3 times, can be lengthy because you have a max discharge rate of 1C, depending on the size of your battery, which means that it can take up to 48 hours to perform each cycle of charge and discharge. So you're looking at 3 times 48 hours for a full profiling. And we can't sit through this in this webinar. But once this profiling is completed, you will have a fully generated battery model in the folder you selected. Let me just abort this. And the battery profile will end up here in profiles. We'll just remove this project. And what I instead will do is I will go here and select one of the bundled profiles from PowerUp and save this in the same folder. That way I can use this in my application for demonstration purposes. And once we have our battery model created, we can go back into VS Code and start working on our application. So for demonstrating how to add this to your application, I will be using the same peripheral LBS sample that we were using in the start of this webinar, and I will just print out the state of charge on a terminal window. And the first thing I have to do is I have to take the battery model I created, and I'll have to copy paste it into my source folder for the app. Like this. The next thing I'll do is I'll go into my apps and I will open this NPM 1300 fuel gauge sample. This is just a standard sample from the SDK, and in the source file I will take the fuel gauge.c and the fuel gauge.h, and I will actually copy paste this into my existing project, into the peripheral LBS that I'm editing now. So this goes into the source files here. You can see we have this battery model already here. I will rename it so it's easier to work with without the parentheses. Then we go into our CMake lists, and then we add this target sources app private source fuel gauge.c. Yeah, fuel underscore gauge.c. And in our main file, we will add some includes. We will include fuel gauge.age. And we will also define a sleep time, which is the frequency of how often we'll call the fuel gauging. Let's call it every second. And then we also want to add the charger. Then we can scroll down to our main loop. Let's see here. And what we want to do is initialize the charger. So I have this already written up. I will just copy paste it. Let's initialize here. And then we also need to add our fuel gauge update. So let's just add fuel gauge update charger. The last thing we have to do is to add the kconfig for using the fuel gauge library. And then we can build. Okay, we got some errors. That's my mistake. One thing we have to do is that we have to change out the battery model that's used in the fuel gauge C file. Let's see here. Fuel gauge C is referring to a battery model, which is not what we want. We want the name of my file, which I will handily copy. Here. And we never ended up using the sleep time because there was already a sleep time in the Let's try again. And we have successfully built the peripheral LBS with fuel gauging included. And then we can program this back into our dev kit setup. And if we now connect to the terminal of the dev kit, we can see that it is actually estimating state of charge on this battery to 99%, and it's decreasing because it's using current. And of course, you can send this data out in any way you'd like. You can send it out over Bluetooth to a connected Bluetooth device. You can show it on a display, or you could configure some LEDs to light up in a sequence that matches the state of charge on your battery. Okay, then I think it's time for some questions. And the first question, which isn't really a question, is it should be #define. Yes, I think I wrote that wrong. I didn't even need the timer, so that's my error. The second question is just to confirm. so it would take 2 days or more, depending on the battery capacity, to fully profile a battery with the fuel gauge board. Yes, that is correct. It takes quite a while. You don't want the battery to charge or discharge too fast. So when you're running through the profiling, it takes longer the bigger your battery is, and also it takes quite a while to ensure safe charging and discharging of the battery. Then there's a question about what solutions we could offer for a use case where a non-rechargeable battery's state of charge needs to be determined across the full industrial temperature range. And for this, we don't currently have a solution. The NPM 1300 is for rechargeable batteries, but if you keep your eyes peeled for the future, we might have something in store for you as well. How do we validate the battery charging error function on the NPM 1300 evaluation kit? Not really sure what you mean by this question. You validate it by getting a charging error when the charging isn't working. But how you would induce such error is beyond my skill set of knowing. Could you tell more about the fuel gauge library? How can the application read charging status and error, and how does it clear the error registers? Well, as a library, it has its API that you call the functions of the library to read charging status and errors, and also you call a function to clear the error register. It's fully documented in the nRF Connect SDK documentation. Then there's a question in the chat, which is, I assume you can't profile for negative temperatures. Yes, I guess that's correct. You don't want to charge the battery when it's below 0. So charging a battery, profiling a battery requires it to be charged, which means that you should stay above the 0 line on your temperature range. Should we fully discharge the battery before profiling? No, there's no need for that. You can start the profiling process at any charge because it will start by fully charging itself, or the battery. Let's see, another question from the chat is it possible to use the system for a non-rechargeable battery to get the power consumption? If you connect a non-rechargeable battery to the battery terminals of the PMIC, you will be able to read out the current going out from the battery in the same way as you would with a rechargeable battery. But it's very important that you do not get an accurate battery profile for your battery, because you can't really profile a non-rechargeable battery with this system. So the fuel gauging won't be accurate. And it also is important for safety that you never enable charging in your PMIC if you connect a non-rechargeable battery. Because we know what happens when you try to recharge a non-rechargeable batteries. Can this product be used with other microprocessor families? I sometimes use other manufacturers' micros. Yeah, it can. It's fully compatible with any I2C compatible microcontroller. If you're using a microcontroller that's supported by the Zephyr RTOS, you can even use the overlays. You might have to modify the overlays a little bit to make them match the requirements of your microprocessor. If you're using a non-Zephyr environment, you can use the npmx library that is found on our GitHub. And if you are not if you don't support the use of libraries, you can always read the datasheet and read what registers you need to send which bits to over I2C to configure the PMIC. So yeah, it's fully compatible with any microcontroller with I2C. Then there's a question about the webinar. Will the recording be available after the webinar? As always, we will have this available online in a few days on webinars.nordicsemi.com and on our YouTube channel. Then there's a question about, is an actual fully functional USB-C connection required for the input to power the PMIC for charging, or can a specific voltage be used? Yes, you can use any 5-volt power supply. It doesn't need to be a USB-C or USB at all. You can, as long as it has the correct amount of current on the input for VBus, it can be used to charge batteries and power the PMIC. And then there's a question, how would we go about integrating this into a manufacturing process? Is the profile for the battery loaded into the PMIC from the app on the radio every time it boots? So I think this was answered by the last part of the webinar. You export the overlay and you build it into your firmware. And this firmware is then flashed or programmed onto your microcontroller during manufacturing. I haven't been into manufacturing myself, so I don't know exactly how this works. But you have these settings are loaded to the PMIC from the microcontroller or SoC because it's hosted in the code of the SoC that's programmed during manufacturing. Is there a capacity limit for this IC? Is there any reason that it could be unable to use, for example, a 5000 milliamp hour battery? No, there is no capacity limits except for the voltages. The only capacity that would affect you for a 5000 milliamp hour battery is that charging current is limited to 800 milliamps. So to charge a 5000 milliamp hour battery, you would be looking at 4 hours of charging or so, which for some application is completely reasonable. And I would encourage you to use this PMIC if that's something that your application can live with. See here, during the charging process, does the library estimate the current charged percentage by some sort of configured charging current and time? Or maybe it briefly interrupts the charging process to read actual battery voltage. Let's see, what is the maximum current that the buck converter can deliver, and what is the maximum current that can go through the fuel gauge? This is a good question. So the maximum current that the buck converter can deliver, it's 200 milliamps per buck. So each they can deliver 400 together, but they have to be split up in 2 loads of 200 on separate bucks. The maximum current that can go through the fuel gauge is only limited by the input current limit of the PMIC, because you have to have it go through the battery input to be counted towards the fuel gauge, and that is at 1340 milliamps, if I'm not mistaken, or something in that vicinity at least. So 1.3 amps. Let's see, from my initial evaluation done beforehand, the whole battery profiling was tied to nRF power profiling tools. Are there alternatives to generating profiles? I don't think there are currently any other profiling options available. We are using the NPM fuel gauge board in addition to the NPM 1300 evaluation kit, which is, I think, the most cheapest, cheerful, and easiest way of generating any sort of battery discharge curve. You could spend a lot more money on a lot more high-end equipment and get the approximate same result. So I don't have any viable alternative to offer for this. Does this PMIC support other battery chemistries beyond lithium polymer? Yes, it also support lithium iron oxide batteries. So LiFe. PO4. Then there's a very long question that I saved for last. Is the chip ready for charge from W sources, USB and PV panel? According to this link, and this might be a problem. Okay, so PV is photovoltaic, I assume. And this looks like there's a question on DevZone. Okay, so the NPM1300 is not created for using solar charging. The voltages that you would come across and the currents are, it's not what the PMIC is intended for. So you would like to have a stable 5-volt source or something in that vicinity to charge a battery with the NPM1300. Are the battery profiles human readable / editable to make adjustment or even try to extrapolate some rough estimate of the SOC of a battery given the voltage? I am not sure. I haven't investigated that much into what is in the .inc LUD files that are generated by NPM PowerUp during the battery profiling. You could always download the app and save one of the one of the bundled profiles like I did in this webinar, and you can see what's inside the file for yourself, and then you can determine if you think that that means that it is human readable or not. I haven't gone that much into that because I am not very concerned with I don't think I will be able to get a better results than the automatic profiler by doing manual adjustments. There's someone who asks if it's okay to use a primary cell battery. Yes, of course it is okay, but you don't get the fuel gauging because you have no way of profiling your battery, or the profiling doesn't support it. And you will also need to make very, very certain that you never try to charge the battery, never turn on the charging functionality of the PMIC if you use a primary cell, because we know what happens when you try to charge a non-rechargeable battery. Is it possible to profile the battery with the negative temperature? I believe not. I don't think the PMIC supports even charging at negative temperatures. What is the maximum voltage of the battery that can be charged? So the maximum termination voltage of the NPM1300 PMIC is 4.45 volts. This is found on lithium ferrous oxide batteries, among other things. Thanks all for watching. I hope you sign up for more Nordic Tech webinars at webinars.nordicsemi.com. This is also where you will find the recording of this webinar tomorrow or the day after tomorrow. And have a nice day, everyone.